Hello, it's me, and I wanted to get into a couple of concepts that I've heard people ask me about regarding the solve strategy of all the different kind of cuboids. So what I have laid out here is I have the most simple version, the 2x2 versions of all the different types of cuboids, starting with its base cube. So what is a cuboid and how does it relate to the base cube, starting off with a 2x2? Now in the Back to Basics series I defined what a 2x2 is. It's a corners only puzzle. You only have corners here. Somewhere deep inside, I don't know if you can see this here, but if you look at any 2x2 that you have, deep inside you see this area that is still or sometimes moves along with the side, but it's a center. I don't know if you can see that in here, but this little thing with a screw in the middle of it, that's the centerpiece. It's hidden, it's buried, it's not really involved in the solve. And between two centers, which you can't see here, maybe you can see it a little bit, you have an edge piece. That edge piece allows for pivoting from one face to the next. And on either side of an edge, joining three sides together, so either side of one edge, joining three sides, are the corners. So 2x2, a simple puzzle, is a corners-only puzzle. So what happens when we broaden that out? What happens when we add pieces to it? Well, the essence of what a cuboid is it's a base cube that have pieces added to it that causes variable degrees of bandaging. So when you look at, say, the next one up, which is a 2x2x3, the basic difference between these two is you've got this extra piece over here. And what is this extra layer? What does this indicate? Well, at the top it looks just like a 2x2. You got the top and the bottom. In between you've got extra pieces, which are not corner pieces. So in here, also deep in here, you've got the true centerpiece, which is buried. And then you've got edge pieces here. But across here, this layer, these are actually edge pieces. So in addition to the corners only, you've now added edge pieces. And what's more, you've added something to what I would call the parity of the puzzle. I'm going to talk a little bit more about parity later, but suffice it to say this is more just kind of introducing the concept. So in many ways what this is this is a bandaged version of this, where I can make 90-degree turns. Here I can't. I can only do 180-degree turns this way. And that's because what a cuboid is, what a domino is it's a puzzle that is the superposition of two parities. So I guess I should define what I mean by parity right now. Now normally when people say the word parity, they naturally assume it means a problem. That if you see a situation that's difficult to solve, they say that it's a parity because you have to do something fancy with it. But in actuality, what a parity refers to is it refers to a characteristic that all puzzles have. So you can't say that certain puzzles have parity and certain puzzles don't. Every puzzle has parity. Parity is just a characteristic of the puzzle. It's like saying someone has a temperature. Well, we all know that means it means the person has a fever, but everybody has a temperature. You can't say that a temperature is a bad thing. Or to say that someone has TMJ. Well, TMJ stands for temporal mandibular joint, but when you say they have TMJ, it means they have TMJ dysfunction. But everybody's got a TMJ joint, so everybody's got TMJ. But what people mean is that when someone says someone has a temperature, it means they have a temperature problem. Or when someone has TMJ, they have a TMJ problem. So too, in solving a puzzle, if you say it has parity, what you really mean is that it has a parity problem. So what's really meant by parity? Well, parity is the characteristic of a puzzle. In most cases, what we mean is it even or is it odd? The characteristic of evenness or oddness is the parity of the puzzle. So this puzzle has parity. It's got even parity. This puzzle also has parity, this 3x3. Now you might not have considered the 3x3 as having a puzzle with parity, but it does. It's got odd layered parity. What's actually meant by parity when solving is really a parity problem. That's when you've jumped from one parity to another. That you've taken a puzzle, reduced it from a certain parity like an even layer parity, and reduced it to an odd layer parity, and you're trying to solve it like that. Again, more on that later, but basically, as we're looking at the definition of what these cuboids are, starting off with the base 2x2 with even layer parity, the first type of cuboid is what I would call a domino. So strictly speaking, a domino, if I were to use it in mathematical terms, is a puzzle of the form of n by n plus o by n plus o, or n by n by n plus o. where O is any odd number. So examples are 4 by 4 by 5, 5 by 5 by 6, 6 by 6 by 7, 7 by 7 by 5, 5 by 5 by 4. So basically what that means is you have your base puzzle, and then you have an odd number that gives you at least one above that. So you're mixing two different parities. So a domino will take your base puzzle and add an opposite parity on one of its sides. So with a 2 by 2, we've got a 2 by 2 by 3, or a 2 by 3 by 3. So that's what a domino is. Now, what a domino means is it's the superpositioning of two different parities, right? You've got even parity on one side, and you've got odd parity on another side. Even parity on one side, odd on another side. If I wheel this guy out for a second, a 3 by 4 by 4, odd parity on one side, even parity on another side. So even, odd, odd, even. Maybe I said that wrong the first time. But in any case, because we have the superpositioning of two different kind of parities, that's going to impact the solve strategy a little bit. So that's what a domino means. Now let's kind of unpack that concept a little bit. Focusing on the 2 by 2, the 2 by 2 scramble, a non-shape-shifting, 90-degree in all directions scramble, corners only puzzle is a pretty simple, pretty straightforward solve, as long as you understand the concepts of how to solve these puzzles. So to solve this corners only puzzle, a couple characteristics to bear in mind. If you're to solve the baseline cube, I have a choice of where to put my sides. So let's say I have the green piece over here. I want this to be the green side. It doesn't have to be here. There is a center over here, but this center does not guide me at all. It's all guided by the corners. I can make this the green side, this the green side, this. It really doesn't matter. So that's the characteristic of an even layer parity, is I have hidden pieces. A puzzle with even parity is simply a puzzle that has hidden pieces, hidden centers and hidden edges, and it's all corners. You're going to find that with every even layer puzzle. Now you may say, well, what about a 4 by 4? Don't you have edges there too and centers? My contention is not really. The true centers and the true edges are buried underneath that you can't see. What appears to be centers and edges are simply specialized corners in center and edge positions. But because you cannot see where the centers are and where the edges are, you don't have a way of coordinating those specialized corners, and can thus get an issue with a parity problem should you try to solve it as an even layer puzzle. Because to call something having edges and centers is something that's characteristic of something with odd parity. So as long as you're saying that it has even parity, you're telling me there's hidden edges and there's hidden centers, everything else is corners. And if you try to force the definition of an odd parity puzzle that has revealed centers and corners onto an even parity puzzle, which is hidden, that's when you might run into trouble when you're trying to solve, because the true parity of an even puzzle is hidden. So basically the solve of this, again, straightforward. I'm just going to arbitrarily say this is the green side. So I'll find the other green and red, stick it next to this, and that's just a matter of doing my RIDIRDs if you wanted to. That's stuck into there. Now again, I assume knowledge of how to solve the baseline cube, but just in case you'd like to see it anyway, this green needs to come into here. So I can make that happen like so, and then the final one here, RIDIRD is all you have to do. Then we get into the dilemma of the last layer. You place this, use the orientation of your choice. Again, I can refer you to previous tutorials on how to solve a 2 by 2 to bring this up. You can just do RIDIRD to bring all that in, or you can do certain shortcuts. But in any case, RIDIRD. This is not how to speed solve the puzzle. This is just how to solve the puzzle. Anyway, so these are all up. Once I have this here, I can do corner swaps, and the corner swap is 2R, U, 2R, UI, 2R. Rotate the puzzle, 2R, UI, 2R, U, 2R. I now have these two corners in, line them up where they're, well, supposed to be, next to this white over here. Move it to the left side, and then once again do a corner swap, 2R, U, 2R, UI, 2R. Rotate counterclockwise 90 degrees, 2R, UI, 2R, U, 2R. Hopefully that didn't move too fast, but again, I am assuming knowledge of how to solve this. This is really just to hit the concepts of what we're talking about. So when dealing with the scramble of the two forms of dominoes, now even though these have different looking structures, I still classify them the same. I classify them the same because they happen to move exactly the same. They're n by n by n plus o, or n by n plus o by n plus o, and they're solved pretty much the same kind of a way. Now what we've done here is we've added something. Because I can't turn one parity into another parity layer and make another 90-degree turn, I'm stuck with 180-degree turns. So the thing about dominoes, because I'm mixing parities, I'm doing the superposition of two different parities, I can't make 90-degree turns by mixing an even parity with an odd parity. I can't do that. So the scramble of this is basically left to doing 90 degrees over here, 180 degrees over here, and 90 degrees over here. So you can mix and match and turn. Again, this is more review to just kind of get into the concepts. Turn, turn, and you can do whatever kind of scramble that you want here. And turn. Okay, so it's a pretty nice scramble. Same thing with this. This is a superpositioning of two parities, which means I can move 90 degrees in this direction and only 180 degrees in this direction, which means that this is a non-shapeshifting puzzle. So dominoes are non-shapeshifters. They're non-shapeshifters because I'm limited in what my scramble can be. Now this is a little more unusual because this one added edges, this one adds centers and edges. So that's why you can't mix these two with each other. So the solve of these guys is going to be pretty much like the solve of just doing a 180-degree scramble with this. So if I were to do a 180-degree scramble, this is what I'm left with. And that's really what a domino scramble and a domino solve is and entails. Turn it here, so something like this. Now the next type of cuboid to make mention of, I think, would be the brick. Now I'd use the brick next because this is of the form of n by n plus o by n plus p, such that as in like 1 by 2 by 3, 2 by 3 by 4, 3 by 4 by 5, 4 by 5 by 6, 3 by 5 by 6, 2 by 4 by 5, 4 by 6 by 7, or of the form of n by n plus o by n plus o plus 2, such as 2 by 3 by 5, 3 by 4 by 6, 3 by 6 by 7. So basically you have two even layers and one odd layer, or two odd and one even layers. So basically that's the same form as the domino. So the form of a brick is the same as the form of a domino, where you have, in this case, two even and one odd layer, in this case, two odd and one even layer. This is really the same kind of thing, but what makes a brick different is the fact that the two layers that are either both odd or both even are different. So in this case, like the 2 by 3 by 4, you've got a 2 layer and a 4 layer, which have the same parity, so to speak, but they're of different values. So in essence, what a brick is a brick is a domino that shapeshifts immediately. That because you have 2 and a 4, because I have the same parity, even though they're different layers, because they're the same parity, if I move it in to each other, then I can actually do a 90-degree turn and shapeshift that way. So the scramble of this would be the same as the scramble of these guys, only you start shapeshifting right away. These guys don't shapeshift. So why is a brick considered a different category than a domino if in essence the structure seems to be the same, although the number of layers although the layers are all different from each other. So why is it different? The reason is because when I do the brick scramble, when I do the domino scramble, I end up with extra layers that immediately get bandaged that I can't get access to. So I can no longer access this over here compared with this. With these guys, I have access to all of my layers. I'm not really bandaging anything. I'm limited, I'm restricted with the domino, but I'm not bandaged. So there's no bandaging here. It would be bandaged if I can move this down and then turn it across. So I'm restricted the way I restricted the scramble here, but I'm not bandaged. However, in this case, I am bandaged. So before scrambling a brick, we generally like to do a 180-degree type process here. Now the 180-degree scramble and the 180-degree solve is pretty straightforward and does not have parity. So I'm going to keep scrambling this over here. Now this is different from what I did with these guys. I could have done it the same way. I could have started off with a 180-degree scramble, but elected not to do that at this time. Okay, so there's my 180-degree. And I did that because I want to separate some of these layers out to enhance the challenge, because when I do a domino scramble, I'm going to start bandaging. So this is the first puzzle, the first cuboid, where I not only restrict the motion, but I also bandage it. So now that I've done that, I can start doing a strict domino scramble of the brick. So I'm going to move this 90 degrees, and I have to move this 180 degrees. So I'm going to keep turning it here, like so, like so. Now what you're going to find is that this in essence is turning into this guy over here. This is 2 layers over here, 2 layers over here. I can no longer access these layers here. It's bandaged. And 1, 2, 3. So when we look at the solve of this is the same as the solve of this. The difference is that when I'm done with my baseline domino solve, I'm done. When I'm done with the domino solve of this, I'm not done, because I have extra pieces here that I still have to solve. And those extra pieces are something that goes beyond just the brick solve, or goes beyond just the domino solve, and I have to do a 180-degree solve of that. There. I think we're good. Now notice I'm kind of limited with this middle scramble over here. I added this middle scramble here. This top scrambled with this bottom. This center only scrambles with itself. So too, this only scrambled with itself, so we don't get any shape shifting of this middle layer over here. So there's the brick scramble, shape shifted, but really it was a domino scramble with a little bit of a Rubik 180 scramble to begin with. Now the next one to wheel out, the next type of cuboid, so we've got the dominoes, we've got the bricks, and now we've got this guy. This one I'd classify as just the shape-shifting cuboids. These have the form of n by n by n plus p, where p is any even number. So if it was an odd number, then we cause the superpositioning of 2 different types of parities. If it was an odd number, this is going to be an even number, which means we maintain the same parity on all sides. Because we're maintaining the same parity on all sides in every direction, then what that's going to do is it's going to allow me to turn 90 degrees in all directions. So it'll cause basically movement in all directions and a higher degree of shape shifting. So what I could do is start off with, well, a domino scramble. So I'm going to start off with a domino scramble over here, just to kind of get it in the same form. Turn, turn. So I'm pretending like it's a domino with the same type of restrictions. So right now it's a restricted scramble, but not a bandaged one. And turn. Okay, so not bad. Looks like we're doing pretty good. But now what I can do is I did that kind of a scramble because what I want to do is, as I'm doing 180-degree turns, I'm now bandaging the puzzle. And this puzzle is now bandaged as a 2x4x4 down to its base cube. I can only turn it as a 2x2 right now. So it moves in all directions, which means we're bandaged in all directions, and there's pieces that I just can't get to. All right, so that is a shape-shifting scramble. The next cousin to this, the next kind of a cuboid, is this one. Now this one has a lot of characteristics that may be similar to the shapeshifter, and it is a kind of a shapeshifter, but it has a unique form with a unique type of characteristic. So these I call the floppies. Now the floppies are the form of n by n plus p by n plus p, where p is any even number. Now this was of the form of n by n by n plus p. So these 2 shape-shifting cuboids were a lot like these 2 domino cuboids. The difference is they're solved pretty much the same, and they don't have any extra or special parities associated with it. These 2, not quite so. So what I can do is I can actually scramble this once again in domino form. doing 180-degree turns here. This one is designed, made, created by Ola Jansen. Very smooth 2x4x4, completely proportional. All right, so when we think that we've had enough of the domino scramble, now we can move right into our shape-shifting. Now once we do our shape-shifting, it's going to start to bandage things a little bit more. So I'm going to move this up, move it across here. The way that I do that is I like to do sort of a kind of a scramble where I haven't completely bandaged all sides yet. This will come across here. So this is the floppy, what I would call the floppy scramble. Okay, now that I've done it like this, which is kind of limited, I'm now going to start moving it in all directions. And when I do that, just like with the Shapeshifter, you'll find that I've now converted this, once again, into a 2x2. So this is a 2x2. And the rest of this is a 2x2 scramble. Another reason why I call it a floppy is you can see how it sort of has a floppy look to it. It's very difficult to keep all the pieces in, but this is a very stable puzzle. I've never had a piece pop on me with this one. So there it is. Floppy scramble, the next cousin to this, to the Shapeshifter. Now we get to one of my personal favorites, which is this guy, what I call the ultimate Shapeshifter. This is of the form of n by n plus p by n plus p plus 2, where p is any even number. So because it's an even number, and then the last one is the even number plus 2, we never leave the parity of each side. So in this case, the 2x4x6, it's the same parity on each side. So we don't have a superpositioning of two different parities. So just like the Shapeshifter and just like the floppy, we can move and shapeshift in all directions. But the basic difference between this one and the other guys is the same difference as the brick was to the dominoes. And that is, there are pieces here that you can't get to. So the way to scramble this is we start off, of course, with our 180-degree scramble here. The reason that I'm doing that is I'm scrambling pieces before any of the bandaging happens. So turn, 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 turn. So before I bandage it, I want to separate and tease out all of the pieces. Okay, once I've done that, I want to continue with what's going to be the most challenging of solves. So there's two different ways that you can scramble an ultimate Shapeshifter, and each way will give you a slightly different kind of a challenge. Now in this case, I can now start off with a brick scramble, where I'm taking it, let's get this a little bit more out of sorts here. I can take it over here and do 180-degree scrambles like this, and scramble it like a brick, exactly like that. I can do that, but if I do that, I'm not going to get the same challenge of moving this up. So before I do that, I'm going to go ahead and do some algorithms that I move this up before I do that kind of a scramble. So I'm going to do to R, to B, to U, L, to up, RI, to up, R, to up, to F, R, to F, Li, 2B, 2R. This is what I call the Red Bull algorithm, and what it does is it simply takes these two pieces and swaps them. Now in the case of a cuboid that has a lot more of a characteristic than just any other puzzle, it actually causes this to flip up. So it allows this to come upwards like that. I'm going to do that on another side here. Now having done that, I'm going to go ahead and start my cuboid scramble. So I'm going to move this over here, turn this here, and turn this here. So this is a brick scramble here. Turn, turn, turn. Okay, once I've done what I believe to be a good brick scramble, I'm then going to take this and start my floppy scramble. I'm going to do it this way first so that I'm not bandaging things where I'm just moving it 90 degrees in one direction but 180 degrees across. And now just scramble it up like a 2x2. So you can see I'm restricted and I'm bandaged. And turn and turn. Okay, so that was a review of all the structures of the different kinds of cuboids. So you saw how neat and orderly they looked when they were solved, and here's what they look like when they're scrambled, with the base puzzle in the center over here. So what does this mean in terms of solve strategy? Well, every one of these cuboids has their unique characteristics, but the solve strategy is an incremental process whereby you're slowly getting it to a domino form, a restricted domino form, and solving it as a domino. And that's what we're going to go over next with this, and then go consistently to higher and higher levels of different types of cuboids.